Let's take a look at how to solve this equation. It's an exponential equation because the variable x is up in the exponent. I'm going to start by dividing both sides by 5. Since 5 and 45 are both multiples of 5, this works out nicely. We get e to the 2x equals 9e to the negative 10x. And notice I could do that. I could divide both sides by 5 because the exponents didn't apply to the numbers in front. The exponent only applies to the base e, not to the 5 or the 45, and not to the 9. 9 is called a coefficient. So what I want to do next is rewrite the right-hand side of the expression using a positive exponent. A negative exponent essentially means I'm dividing by the base that many times. So I can rewrite this as 9 over e to the 10x. And notice again, the exponent negative 10x, it doesn't apply to the 9. I would need parentheses around the 9e for that to be the case. But without parentheses, the exponent only applies to the closest factor. It only applies to e. Of course, on the left-hand side, we still have e to the 2x. So rewriting the expression in this way can make it easy to see that if I multiply both sides by e to the 10x, it will cancel on the right-hand side, but that e to the 10x also multiplies with the left-hand side. So I get e to the 2x times e to the 10x equals 9. Of course, now we can add these two exponents together. Since the bases match, I get e to the 12x. And having a single exponential expression on the right-hand side equal to a number, I can rewrite this using a logarithm. The equation is equivalent to 12x equals log base e, or natural log, of 9. And so we can divide both sides by 12 to reach a final answer. And that's a pretty good place to stop, but we can make things a little bit simpler if we notice that 9 is a perfect square. 9 can be rewritten as 3 squared, which means that this equals natural log of 3 squared over 12. And that exponent, using the power rule, I can bring that exponent to the front and then divide this 2 with the 12. So a slightly better final answer would be x equals natural log of 3 over 6. Now let's revisit one of the key concepts in this example. If I have an expression like a times b to the negative n power, I can interpret this exponent negative n as representing how many times I want to multiply by b. But because it's negative, it really represents dividing by b n times. So we can rewrite that exponent as a over b to the nth power. Notice that a stays in the numerator because the exponent only applies to the closest factor. It only applies to b.